Hey guys, this is Brad Dyke talking to you about a little bit of hardware stuff, and I'm going to talk about something that people have asked me questions about, and that is heat, and more heat, unfortunately. Hate to say it's true. And why is it so important to understand? Well, right now we're going through 95-degree weather outside, so that means it's right now, about 98 degrees in this room. I mean, I have all my gear turned off, everything's off except for one particular switch. But everything else is off because I don't want to spend a fortune keeping this room at 71 degrees while it's so hot. So that's why it's kind of quiet in here today. But the key thing is heat. Heat has always been a problem for me in data centers because when I have to deal with it, it costs a fortune to keep IT equipment cold, or at least temperamentally in the right temperature. We have the exact same problem with laptops, PCs, and so on. And when the introduction of heat pumps came into existence, this guy right here is a heat pump. What it is basically is there's a gas that on one side kind of goes pseudo fluid, and on the other side it goes gaseous. And it cycles around and around in a way so that it can transfer heat more effectively than just simply using a static passive heat sink. So when we deal with heat, we have to understand that heat happens in two phases. One, high temperature, and then two, transport temperature. Transport temperature is when you're looking at a heat, here is where the heat is really, and here's where the heat isn't. But you want to move that heat out to here to get yourself in a good place so that these aluminum threaded heat shields can start dissipating the heat by blowing air through this on a fairly fast volume to allow you to cool down that and get that gaseous state to go back into liquid down to the bottom again. And in this particular case, we have what's called two set coils here. And two set coils basically means that you have a loop that comes down and it loops twice. And it's a really good heat sink opposed to a single set coil, which only has one set of coils sets, and that's it right here. Starts on one end and ends at this other end. If you look here, you will see that there are a total of 4 sets on each side with 4 sets of endpoints here. And as I said, when the liquid gets away from the heat source, it transforms into a gas, moves out, and then gets condensed and then comes back down and again goes for more heat and pulls it out. Now, the heat pump system you see right there is a heat pump. And what is a heat pump? Well, a heat pump is really known as a TED, thermal electrodiode system. It's very similar to this, except it has a piece of electronics on it that uses electricity to move the heat faster. And you can use the electricity to transition the direction of the heat. Think about it for a second. So in my data center here, that little guy down there will cover this entire room plus 20% more, which means basically I want to run it at about 50% capacity. By running at 50% capacity, that unit will run me for 10 years. If I got my square footage too close to how many BTUs this guy can handle, I will have the lifespan of a 2 to 3 year window because I'll be running it harder and wearing it out faster. It's just the same principle as we do with hard drives and everything else. So what's important to understand is when you're dealing with heat, you have to understand that you could put as much heat into the room as you are trying to get rid of the heat by introducing motors, fans, and so on into the equation to move out the capacity of the overall heat that you're dealing with. So with that being the case, we try to use these guys. See that little micro fan there? Opposed to using a big engine fan. Now, yes, the big engine fan can move a lot of air, but the motor is generating BTUs of its own heat, which you have to deal with as well. Same situation with your cooling units. They make their own heat. The good news with them is they have an exhaust port to funnel the heat out of the room and keep it localized. But the other good news about that is it pulls air outside to circulate that hot air opposed to taking your cool air out with it, which is very important. Now, with that being the case, the next component is doing it better. So what is the better way of dealing with heat? Well, whenever you see a piece of appliance and you open it up and all you see is a heat sink, a passive heat sink. This is a passive heat sink right now because there's no fans on it. So it's not active, it's passive. It is using a heat pump technology, but it doesn't need to do anything special because the metal is able to not only take the heat off, but take it off in surplus. So when you have these different heat sinks, and depending on how many aluminum blades you've got in here, will dictate what type of heat threshold can be done. Others have alluded to using more structured approaches where they have a fanning effect. Now this fanning effect supports what we call convection. Unlike a very asymmetrical design, squared, human design. But if we look at how nature expels heat, it doesn't expel it in single blocks. It expels it like this, outwards, because heat expands, right? So with that being the case, that's why some of these fans are so impressively capable of doing stuff. This one does have a fan in it, but it's not needed, technically speaking, because of its ability to take care of itself effectively. This is a very, very good heatsink. Passive heat sinks are the best, but the only way you can do that effectively is by using a tool. Let me see if I can find it real quick. Yeah, here it is. Using a tool that will allow you, and this is it right here, it is a thermal device, and what it will do is it will give you the ability to hit an object, let's say a microchip, look at it, gauge its heat, and it will come out with an output on it to show you how hot it is, and then you can use a mathematical equation set and order a special heat sink that's designed to suck off that much heat plus 20%. I always do it that way. It's a little bit larger heat sink, but hey, why not? I mean, it keeps the chip happy, right? So that is the best way of dealing with heat. But with our industry the way it is, we all want to maximize and triple and overclock and, stress out things. So what you're actually starting to see on motherboards is heat sinks that are on the motherboards like such. Let me show you one that actually are more than they need. So if you look here, here's a heat sink right here. And these heat sinks are more than these chips really need, but you don't know if you need them or not. And there's another one right there. But the whole key thing about these heat sinks is the manufacturers don't know what you're going to do. You're going to overclock, or you're just going to do something electronically wise is going to generate heat more than that's normal industry inspected. So the easiest answer to that is put a heat sink on it that's more than it needs. So let me put this down for a second. So the key detail here is when you're dealing with the nature of things and you want to make it work better, and a great example of making things work better, which I love, are Raspberry Pis. These little suckers right here. You see, these guys have heat sinks, but they have heat sinks because I chose to put it on it. A Raspberry Pi can work without a heat sink. Not very well. It will throttle because there's no way to get rid of the heat. So it's a great thing to experiment with. So that's something I recommend you guys to do. Have some fun with this. You can open up stuff, take a look at it. These heat sinks don't cost a lot. Aluminum heat sinks, and they have this little silicon dioxide adhesive that both sticks and acts as a heat transfer. That helps you move the heat off even better. Now that does heat up the air. And if you guys remember my discussion about racks, there's a reason why racks are painted with a plastic polymer. It's to keep the heat that comes from the racks equipment, i.e. servers, hard drives, whatever, from becoming embedded into the frame of the rack itself. The rack would act as a capacitor and would hold the heat until it was subjected to cool air enough to pull the heat out of it. Hence, more heat, right? And that's not good. So the value there is, how do you defeat such a thing? Simple. Turn on your HVAC and bring the temperature down to the proper environment you want, then power up your equipment. By doing it that way, you have a power curve of cool air fighting against any future growth of heat capacity, which heat capacity has nothing to do with the temperature, but is actually a medium that can hold heat. just like a battery holds electricity. Everything can do that. Matter of fact, that very principle is how you make these guys work so well. But with that being said, I thought this would be a cool little video to talk about something that people were asking about. And how do you deal with heat in your IT lab? How do you offload it? How do you get smart about it? And the fact that you can use concrete, a concrete slab that's on the earth, as an added value because it's a cool temperature source to add to your HVAC environment. It can create what's called a true convection effect, and so on and so on. Many of my videos talk to this, and please feel free to look at this. They talk about the fact that any type of heat source that which you truly want to address, make sure that whatever you put on it can do it 100% plus 20%. That's right. So a heat sink that goes on will handle the temperature at 120% opposed to just 100%. Because if it's just 100%, then you're not technically truly pulling heat off. You're just taking the heat. Anyways, this is Brad Dyke saying goodbye. I hope you guys have a great week. You take care and God bless.